So today what I would like to do is work through the Mercury Tectonics field trip that you have access to through your Canvas account. And that if you log on with your Mississippi State email to Google, you'll be able to get in here and type on and then share with me. This is also available in your packet that you could have picked up outside of my office on Monday or Tuesday of the week we returned from the 2-week spring break. If you are doing this from home and you're doing it electronically, you'll find that you don't have the ability to edit this document. So what I would like you to do is click File, make a copy, and you're going to say that it is a copy of Google Mercury Tectonics field trip, but with your last name first. So just for example, I have now put in my last name and the Mercury Tectonics field trip, and then you're going to choose to share it with me at the end. So click OK. This new document should open. You will click Share. And then in here, you'll type in my email address, which is ktw202@msstate.edu. Make sure that I have editing privileges, so that means that this little pin is turned on. Here I can comment, here I can view, I need the ability to edit, and then you're going to press send, and that's going to allow me to see the work that you've done. For now, I'm just going to cancel that because I don't see a point of sharing it with myself. So let's follow the steps. Google Messenger Quick Map and click on the Quick Map. Messenger is in all caps because that is the mission to Mercury. It stands for Mercury Exploration Science. I don't know. Honestly, that's terrible, and I worked with Messenger data for a long time. Okay, Messenger Quick Map. We click on this first link. So what you'll notice is that this is kind of like the Google Earth or the Google Mars, but for Mercury. So that's what this step says. On the left-hand side, you have choices about how to view the data. So we're going to click on this little globe right here where it says Switch Projections. And we're going to choose Mercury Globe 3D. What that does is it gives you the ability to rotate the whole planet. So I'm going to click this again to reduce that, and now I can rotate Mercury. Notice down here I have latitude, longitude information. So I can go up near the poles. There's also these nice crosshatches at the North Pole and another one at the South Pole. Right? So it says zoom out and click and drag to move the planet's surface. So I click, drag, and I can move the planet around that way. Click on the hamburger, the 3 horizontal bars. That's this one where it says layers. And under the XRS composition maps, make this a little bit larger. Under XRS composition maps, we're going to turn on each of these individually. So just to be clear, when you click on layers, there's instrument footprints, which just show you the coverage. So where has data been collected? That's what the footprint means. There are location overlays. Right now, nomenclature, so the names of things are turned on, but we could also turn on these other things. For now, I'm going to leave nomenclature on. These are things that we see from Earth, but there's all of this other information. So XRS composition map tells us about the composition of the planet. So let's click on and off each of these. This is the aluminum to silicon ratio. And if I click the little I, it's going to give me the scale bar. So at 0, there is no aluminum for the silicon that's there. So these are low aluminum regions. We compare them to silicon because that's the most common element on the surface. So by looking at these other elements in relationship to that, we can tell where we have areas where there's a relatively high amount of each of these things. So red is going to be high aluminum regions. Here's a really high aluminum region going into the brown. Okay. Really, really high. Right? Calcium to silicon. This one doesn't have full coverage, but it has a little bit. Ooh, what's going on there? A facula. So if you aren't familiar with the word facula, it means a little vent. So this is like a little volcanic feature, and it looks like that's enhanced around that volcanic feature. Let's go down here. There might be a vent in here somewhere. Maybe that? Don't know. I've never looked at that data individually. Whoa. There's a really high calcium area. I wonder if that's the same place that the aluminum was. Nope. Low aluminum. All right, iron. High iron in that area. Low iron over here. Magnesium. Got a couple high. Whoa. There we go. That's a high magnesium region. About the iron in that area. High iron. High calcium. Cool. And so now let's answer this question. Silicon is the most common element in rocks, so we compare these other more rare elements to the amount of silicon to learn where unique compositions on the planet are located. Turn on the magnesium to silicon. The amount of magnesium in a rock tells us if the rock is relatively old or young. So magnesium is an element, and this is true for Earth and other planets. Magnesium is most commonly found in the mantle. It's like iron. So magnesium and iron are heavier or denser elements. So when a planet is forming and differentiating or organizing itself by density, magnesium and iron tend to get kind of sequestered into the mantle. But if you see a lot of magnesium at the surface, it tells you that that's really, really old crust that actually cooled directly from those mantle compositions. So over time, a surface gets what we call reworked. And these areas are places where there hasn't been a lot of reworking, that really old first cooled crust with the high magnesium and iron composition is preserved. So can we find the high magnesium region? Yes, it's right here, and it's centered at 21.2 degrees latitude and negative 81.2 degrees longitude. I got that again from looking down here, so that's about where it's centered. All right, step 5, turn off magnesium to silicon. Under terrain elevation, click USGS. So terrain elevation, USGS. Click on the information button next to the USGS symbol. What is the lowest elevation on Mercury and the highest elevation? So this scale bar is going to tell us the lowest elevation and the highest elevation. So it's about negative 5.12 kilometers. That's the lowest elevation, so about negative 3 miles below Mercury's version of sea level. And this is about 4.2 kilometers, so just under 3 miles for the highest elevation on Mercury. Where is lower topography concentrated? So what we're going to do to figure this out is rotate the planet until we see lots of dark blue. Okay, this is some high topography. That's pretty dark blue. Whoa, that's a lot of high topography. Okay, so now I'm rotating toward the South Pole. I see a lot of blue. And same thing during the North Pole. So, and this is actually pretty low terrain too. So where's the lower topography concentrated? To me, it's concentrated near the north and south poles. That's where we see a lot of that blue. Turn off the lower elevation layer, or sorry, turn off the elevation layer. Under MDIS, Global Mosaic Campaigns, down here, MDIS is the Mercury Dual Imaging System. Click on 3-color high-resolution Northern Hemisphere map. All right. This is actually what Mercury more or less looks like. This is close to a true color map of Mercury's surface. A good key to understanding this is that light stuff, so these streaks, light stuff tends to be young and dark stuff tends to be old. So this would be an old area, but these are a little bit younger. This is an enhanced color, so some of the blue, like this crater right here, Degas, that looks blue, that's not really blue. It's just it's enhanced color. It's to help us see differences in age and composition. So now we're going to go back. We're going to change the projection to equidistant cylindrical. And we're going to locate Pantheon Fosse, which is at 30 north and 162 east. So down here where you have negatives, negative longitude is west, positive longitude is east. So we're going to go to 30, and we're going to go over to the east to 162. There it is, Pantheon Fosse. Okay, Pantheon Fosse is all of these fractures. And I think it's easy to get the right sense of motion with the color on, but if it helps you, you can turn that off. See how it just looks really intense to me? It almost makes these look like they pop out. I think it looks a little bit better in the 3-color. I wonder what the 8-color looks like. Ugh. Okay, so you can see all of these fractures running through here out of the center of this impact crater. So this is a really large impact crater called Caloris. It's the largest impact crater on Mercury, and it defines the calorium time system for Mercury. And right in the middle of it, we have these fractures that kind of radiate out from the center. So what do you think these linear fractures are? Are they more likely to be normal or thrust faults? So if we look at some of these, see how this middle area is dropped down and these sides are raised up? When you see topography that decreases, that lowers, then that's how you know you're dealing with normal faults. So these are probably, if you've heard the term graben, these are probably graben, where these sides are the sides of normal faults. Okay, so let's see. Turn off the 3-color mosaic. All right, it's really intense. They might look like they're standing up to you. So the way to fix it is to go up to Apollonius, no idea how to say that. All right, look at its central peak, make the central peak come up, and the rest of these should then drop down. You can do the same thing with the rims of these craters. So this rim should come up, this rim should come up, those streaks should drop down. Zoom out until you can see all of Caloris Planitia. Right. So this whole thing is Caloris Planitia. It is the largest impact crater on Mercury, and the Planitia just means the plains. So this area, there was an impact crater. That impact crater has flooded with volcanism, and so these are actually nice plains of volcanic deposits that have filled the inside of this impact crater. So the impact crater's name is Caloris. The plains within that Caloris impact are called Caloris Planitia. All right. Can you find concentric thrust fault related landforms? So look at Caloris. Try to make the area near Pantheon Fossae the center of a bullseye and see if you can notice rings that come out away from Pantheon Fossae. What process do you think formed these thrust fault related landforms? Let's zoom in on some. So there's these faults right here that are opening mode fractures or that are cracks or normal faults. And then we've got these that are thrust fault related landforms. So notice that a normal fault related landform makes negative topography and a thrust fault related landform makes positive topography. So here we've got positive topography. Here's a mix. This is a weird area that combines normal faults and thrust faults. Right. So what makes this is a process called subsidence. So let me open up a place to draw. All right. Let's say you put in a wall here, right? And let's put in a wall over here. And then let's say that you have friends and you decide that you and your friends are going to play a game. Okay, these are your friends' heads. Each of you gets a body. You're only going to get one leg in this scenario because I'm not going to draw this 3 times. Okay. So here, the game is that these friends on the edges of the walls get to hold on to the wall. And you guys are going to hold hands with them. Okay. The problem is there's not enough friends to stretch this whole distance. And so what's going to happen is we're going to have some situations where we create gaps like this. So this friend right here, their arms would be stretched so long that they might break, that this hand-holding process breaks. And so that forms those normal faults. What this would be analogous to is these are the walls of the impact crater. You all are the fluid, the magma or lava that floods the impact crater and makes these plains. But because the edges of the impact crater are colder, the lava that touches these outsides of the crater, the edges of the impact crater, that lava freezes first. That becomes the most stable first. And you end up with this soupy mix of lava in the middle that's not frozen onto the sides, it's not attached to anything yet, and it just floats. And as it floats, it also cools in the middle. And so you get kind of a cold spot here, a cold spot here, and a cold spot here. And this area in between cracks and opens up. Now the other thing that happens is that this also creates a space for the very edges of this material to want to ooze down into. So this friend can slide down and keep sliding down and keep sliding down if it detaches until it's basically on top of your other friend. It smushes them. And what that creates, that smushing process, creates the thrust fault related landforms or the high topography. So that high topography is reflecting this shortening process of your friend smashing into your other friend. And the normal fault process is reflecting this friend detaching from these other friends. So you can imagine that we get these two things together happening at the same time and kind of happening in opposite directions. So that's why you have thrust fault rings that are concentric, but then you have these radial patterns of normal faults that open up away from the center of the impact crater. Okay, so what processes form these within the crater? The smushing process of some of the outer layers on top of the inner layers once they've cooled. West of Caloris, find Rotlati crater. So this is number 11. We're going to zoom out. If we go west of Caloris, we can find Rotlati, or Rotlati. This is a multi-ring basin, so here's the inner ring, here's the outer ring. Zoom in on the crater. What are the structures within this crater? So what I want you to do is ask yourself if these are negative topography or positive topography. Okay, hopefully you said negative topography. Those are little down-dropped regions. So these are normal faults. And clicking on and off the West illumination map might help you. So under MDIS Global Mosaic Campaigns, click on West illumination map. Sometimes the west illumination map where the sun is coming in from the west can help people see this a little bit more sharply. East usually muffles things, but here I think the east makes it look a little bit better. Okay. Southwest of Rotlati. Oh, and here, this is that situation where you have a cool ring, right? This would have cooled first. Then everything got flooded with lava. The lava crystallized along the edges first, and as this center part cooled, it kind of cracked and detached from the edges. Some of you may have made a cheesecake. This happens with cheesecake, unless you keep a warm water bath on the outside of your cheesecake to kind of keep the temperature stable. All right, southwest, look for Beagle Rupees. Beagle Rupees is going to be around 2 degrees south, latitude, 2 degrees south, and 100 degrees in longitude. Now, notice that Beagle Rupees is not an impact crater. Beagle Rupees is a fault, or a fault-related landform. Click on the Draw Search tool. So here's the Draw Search tool. Choose the Arc tool, that's this middle one. Click the left and right of the structure. And right-click to end the line. The screen should display a topographic profile. So this is the elevation of that landform. Is this a normal thrust or strike slip fault? So here, going across the fault, right here, see how we're making positive topography, that we're going uphill? That helps us identify that this is a thrust fault. Find, oh, and if you wanted to, where's topography? You could see that right here, this topography raises up. It's a little bit more orange than this over here, so this is a thrust fault. Find Renoir Crater at 18 south, 519 west, 18 south. South latitudes are negative. 18 south, 519 west. West longitudes are also going to be negative. And we are looking for Renoir right here. This is also a peak ring crater, similar to Lottie. And if you changed your illumination, you can change over to moderate. We can try west illumination. I'm going to keep it at moderate. All right. This impact crater is cut by thrust faults. Which is older, the thrust faults or the impact crater? And think about this from a stratigraphy standpoint, or using cross-cutting relationships to figure this out. You did this with the road and the paint earlier in the semester, that if you're going to see the paint, the road had to be there first for us to paint on. So here, if we're going to see the thrust fault, there had to be the crater there for the thrust fault to cut through. So that crater is going to be older than the thrust fault. The fault cutting Renoir Crater is trending north-south. So this is roughly north-south, but just southwest of Renoir. So to the southwest of Renoir, you should see Simone's Crater and the Mimi Rupes. I think it actually should be southeast. Right here. There's Simonides. These are Mimi Rupes. And these are all kind of trending in this general direction. Sketch the general pattern of craters and structures between Simonides Rupes, Nampeo, and Newman. Here's Newman, here's Mimi Rupes, here's Nampeo. So what I want you to do is just draw these main three craters and then try to draw in that length of positive topography. What that's going to do is give you a general sense of the orientation of the faults in the impact craters. Okay, so I'm going to insert a drawing. Okay, I'm going to go down here to Newman. Doesn't really look like a perfect circle. Nampeo looks pretty circular. Some of this, if you're thinking this is a projection issue, some of this is a little bit of a projection issue. If you were concerned about projection, you can go back to 3D Globe. Look at the same spot. When you start to look at these impact craters in here, what you may start to notice is that they look kind of weird. Like these two right here look kind of elongated like that. This one right here also looks a little smushed. Maybe not as bad as that one. This one up here looks a little smushed. Okay, and the faults are lined up like this. And you'll find your own way to draw this. But this is kind of how I see it for me. Just south of Newman. Okay. Now, these are all thrust faults. Okay. So if we look at the topography, we would see that these are raised topography. I'm going to go back to this projection so we can see this picture a little bit clearer. So what's happening here is we are shortening the topography this way. So this used to be flat, now it's bunched up, so now it's shorter. What that means is that we take things, if we were to take a circle and kind of bunch it up, we would make it more of an oval shape. So if we took a nice circle and we bunched it up this way, same as the faults are going to do, we would make these elongated shapes. So what I'm trying to say is these craters used to be circular. Their shape has been modified by these faults. So that's kind of what we should say in number 15. The orientations of the faults are the same as the long direction of the ovals that are now these craters. That the craters used to be circles, now they're ovals, and the long dimension of those ovals is aligned with these thrust faults. So the thrust faults, which effectively bunch up the topography and take something that used to be longer and make it shorter, they are shortening this dimension of the impact crater. All right. Thank you very much.